Thanks everyone for coming this morning. Today our talk is on machine learning ops at scale. So we're going to talk through a case study that Hubert and I worked through around predicting bus departure times using about 18,000 machine learning models. My name is Gibbons. I'm a technical specialist at Microsoft. I'm on the global black belt team. We focus on cloud native app development, whether that be microservices or containers, serverless, or various event-driven architectures. And then, of course, the DevOps kind of that drives all those guys.
Hi, everyone. I'm Hubert Duan, data scientist at Microsoft in our Canada National AI team. I work with enterprise and public sector agencies in Western Canada on solving business problems through data science and machine learning on the Azure cloud platform.
Yeah, and so I guess before we get going here, some of the session goals that we wanted to talk about today. So we wanted to show you how transit systems are improving the customer experience without actually increasing any of their operating costs. And this is a pattern we've seen in multiple cases of across North America, including the case study that we're going to be talking about today, which is in Vancouver. And then we want to explain what a micro-model service approach looks like. Again, this case study used about 18,000 machine learning models. These are actually all running in production in Azure today. And then finally, we wanted to show you how Azure DevOps was used to operationalize the models in production, along with Azure Machine Learning Service in this case. So yeah, a little bit about TransLink. So as cloud solution architects at Microsoft, Hubert and I we get to work with a huge variety of customers across many industry verticals. And we've been working with TransLink for over 2 years now. A little bit about them. They're the primary transit system in Vancouver. So if you've ever been to Vancouver and taken the bus, you're probably on a TransLink bus. Their transit system services over 2.5 million residents and covers almost 2,000 square kilometers, 200 bus routes, 4 metro lines, 3 passenger ferries. And actually includes the busiest bus route in North America, which I didn't know before doing this. They have a strong mandate and focus on accessibility, sustainability, safety, and then of course customer service, which is one of the things we're going to be talking about today. So, what's the problem we're actually trying to solve? What's the problem TransLink trying to solve here? The stakes of waiting with public transit are actually particularly high because the alternative for the rider, which would be taking the car, requires no wait time at all. And there's been a ton of studies that were done on sort of the psychology rather, of waiting. For instance, when we're told the doctor will see you in 15 minutes, those 15 minutes feel to have passed by much quicker than if we waited the same amount of time, but we're unaware of that wait time. And there was one particular study that was done at the University of Washington. Actually watched people wait for the bus. They timed how long riders spent at several different bus stops, then asked them for their own estimates on how long they felt like they'd been waiting. And many transit users actually felt like they'd been waiting up to 50% longer than they actually had because they didn't have access to that real-time information. So in order to mitigate this perceived wait time and then improve the user perception of the bus system, there was this app that was rolled out in the Seattle area in a county, King County it's called, and it's called the One Bus Away app. And the app gave the users access to that real-time information, essentially where the bus was. I'm not sure if there might be something like this in Toronto as well. And the surveys, so they surveyed a lot of these early users of this One Bus Away app, and 92% of them reported that they were actually more satisfied with public transit as a result of using the app. And of course, King County Metro didn't have to reduce the fares or invest in new buses or even increase their service frequency to get that. They just had to actually add that real-time data. And so TransLink did the very same thing. So you can see on the slide that Hubert's showing, there's some screenshots of the initial TransLink mobile app, but they were still getting actually a lot of feedback, some negative feedback as well. That's some of the tweets you see on the right. And yeah, so they released these APIs using the GPS location of a bus that essentially estimated the time from bus stops in 2012. And this was kind of the version 1 of these APIs they released. These are publicly available APIs. They were consumable through text message, mobile app, web application, and then also published like Google Maps, etc. And they garnered a ton of interest. People like were super stoked on them. They got over like 100,000 active users per month and over 100 million requests per month. But again, they were getting some of the negative tweets, some of the negative feedback that we were looking at the previous slide, and so they decided they need to improve that system a bit further. And so after looking into the accuracy of the predicted departure times compared to the actual departure times, they found that although that the GPS APIs, so that version 1 that they released, although those estimated departure times, like that delay on the app and that real-time data helped, didn't actually entirely solve the problem. They needed a better way to essentially predict that delta between the actual departure time and the API departure time. So on the graph here, you can kind of see there's the blue line, which is the old API, or that V1 that uses the GPS. And then the green line was the actual delay of that departure time for buses. And we were trying to approximate the green line as close as possible. So they decided they need to create some machine learning models, essentially to predict that departure delay for all stops and all trips. And so the reason why they did this, the reason why they decided to put so much work into this was so when customers have access to that real-time data, when they have access to that GPS location of the bus, they had even higher expectations of the transit service than when they didn't have access to that real-time information. So as well as the fact that API v1 estimated time delay, if it told you that it was going to be 0 minutes and it was in fact 9, as you can kind of see on the graph there, the perception that they were waiting for longer got much worse after 5 minutes. And so this delta they kind of called like waiting in the dark. And so the API, although helpful, actually compounded the issue because it was not sufficient enough to solve the problem. So I'm going to hand it over to Hubert quick to give you a quick demo of what is actually running in production today.
Yeah, thank you, Alice. So I'm gonna so imagine that I'm a transit user and I'm at a bus stop. So I'd like to know when my bus number 4 will actually depart from my stop. So I'm gonna go into TransLink's website. I'm gonna go into the next bus platform. So this is the platform that is running completely on Azure. And I'm gonna enter a bus stop number. And then I'll click on how to find when my next bus will depart. Again, I'm on the website, but to Alice's point, the next bus platform, you can access through mobile app, text messaging, first and third party services as well. So here we go. So I'm heading towards downtown. So it's actually telling me that's gonna depart now or in 23 minutes, 39, 54, and so on. So these are actually actually predicted departure times, and all of these calculations is stored and served all within our Microsoft Azure Cloud Platform. So I'm going to go back to the deck. Yeah. So now let's look into how the model approach actually looks like. So as you can see, departure time predictions are given at the bus stop level. So looking at hundreds of bus routes, each with many stops, there are going to be a lot of models. So this is why a microservice model approach was used. So let's see how that looks like. So imagine a user is at a stop and a bus is coming towards it. To predict the departure time, we can predict the run time of how long the bus will take to reach the stop. It's of course going to be based on GPS signal where the bus is currently, so that we can calculate the relative proportion of how far along the bus has traveled from the previous stop. And together, it's the prediction time will take into account the dwell time prediction. So the dwell time is how long the bus will stay at the stop for onboarding times, driver break, and time like that. So for model training, a number of different data sources were used for the model, including weather, schedule, GPS, and very importantly, traffic. So each of these models were trained using the standard XGBoost algorithm in Python as regression models. So the actual model training implementation was fairly straightforward. Now, what the one novelty here is that in practice, users of transit would actually often be many stops away from where the bus is actually at currently. So if we imagine this approach at scale for all the bus routes and stops, there will actually be a vast number of models considered. So the magnitude of this approach is actually in the tens of thousands because there are hundreds of routes, each with tens of stops. And so the number of models would get amplified in terms of multiplication. So each of these run and dwell time models along a route would actually provide time, run and dwell time estimates, and the summation of those would actually provide the predicted departure time. So here are some reasons why these individual run and dwell time models are trained separately. So in the transit domain, travel and dwell times are very important. So they have many different use case applications. So this approach actually provides translating with a rich centralized model registry repository for predictive analytics. So for example, it would be very important to consider for route planning and schedule purposes, especially for new ones that may overlap with existing routes. So here's what I mean. So suppose there's an existing bus route with run and dwell time models as such here, as illustrated. Now, for a new route that's being planned, it may very well overlap with an existing one in some areas. So the existing models can be used for schedule and planning purposes. As new routes are planned very often in a year, these insights could be very important for consideration. Now let's look at the high-level scoring architecture. So overall, it's a service that is completely event trigger based on GPS updates. So for every GPS update from any bus, the service will get all applicable future stops until terminus, together with the supporting data sources for prediction. The models are loaded in memory through virtual machines and use the provided data to predict run and dwell times. Then the predictions are summed up for departure time estimates for those stops, and then cached in a prediction database to serve to first and third parties data departure time providers. So the reason for caching is that, if you can imagine, at a stop, many transit users might want to know the same departure time estimates. So instead of the service having to predict the same time separately for all those users, it can predict one time, cache it, and then serve it to multiple users. So this solution, as Alice has mentioned, has been deployed in production on Azure and is currently running for about half a year, used by all the vast number of transit users in Metro Vancouver. There's actually been a daily Hive article published detailing this project publicly. So one thing to call out is that through this project, the difference of the predicted and actual bus departure time estimates have actually been improved by 74%. And another metric that we can share here is that the average customer actually can spend about 50% less time waiting for the bus because the predictions are more accurate. So in other words, because they're more confident of these provided departure time estimates, they can actually arrive at the stops closer to departure time. So now let's look at how the process runs in production with model training and deployment. So just as a side note, at Microsoft, we often use this word operationalization. Most of us find it very hard to pronounce, but what it details is the process for deploying models, machine learning models into production. So the initial training and pre-processing for model training is done through a batch process. So the process includes a number of steps. So first, multiple data sources such as weather, traffic, actual schedules, and of course GPS are loaded, ingested into Azure through a service called Azure Data Factory. It orchestrates data movement, normally from on-prem and other data sources, consolidating them into the cloud Azure platform. These data sources land into a cloud SQL database, and then infrastructure as service with Azure virtual machines are used for training at scale. Then Azure machine learning is used for model management. So the models through XGBoost are fairly compact, so they are serialized into Azure blob storage for in-memory access. And quickly, I'll just provide a quick introduction. So Azure Machine Learning Service is our end-to-end Microsoft machine learning platform on the cloud. It empowers users to bring in AI with an end-to-end machine learning experience. So it would have components, including automated machine learning, deployment, a Python SDK, of course, integration with DevOps tools and processes. So now in production with this many models, you certainly would not want to train them manually. So we need an automated way to accelerate and get the process done for model retraining. So now I'll pass it over to Alice.
Yeah, thanks, Hubert. So as Hubert mentioned, we had a batch process do the initial training of the 18,000 machine learning models. But we need to add some additional process around sort of that retraining and deployment, because as you can imagine, that's a lot of models to manage, retrain. So some of the requirements that Translink had, they were really focused on this custom data drift monitoring system. So this was a system that Translink had built in-house and essentially would selectively choose models to retrain because that training data had, the distribution of the training data had changed significantly since the previous training was done. They also required a centralized model registry, and then of course some good model performance monitoring in order to track and manage just that sheer amount of models. And then another requirement was that Translink wanted to automate that end-to-end machine learning lifecycle. And this included some of the pieces like on-prem data ingestion they had. So they weren't full cloud environment. They had some of their data still living in a data center. And then a few data transformation, data wrangling steps, and then of course the actual retraining and deployment they wanted to automate as well. So some of you might be familiar with the MLOps lifecycle. I know there's a ton of variations of this in the machine learning MLOps community. That's what this conference is about. So the one that we used, it just is on the bottom of the screen here. It's fairly basic. Came up with the process of like sort of developing and training that model. Obviously, this is in a reproducible and repeatable pipeline that we used, and then packaging up that model in a programmatic way with various metadata as well, and then validating that model. This is a big piece, so ensuring that it is producing kind of the values or the expectations that you have. We had some manual checks in here from some SMEs at Translink, and then deploy that programmatically. So across our environments, we had multiple environments, QA to prod, and then one of the most important, which I think gets forgotten a lot, is that model monitoring and the performance monitoring. So ensuring that kind of when to replace, update that stale model, and then ensuring that the model is still useful from a business value perspective. And so we decided this is a great chance to use like a pretty heavy MLOps process based on the number of models that were being accessed, of course, publicly. And so we used Azure DevOps. I'm not gonna, this is hopefully not a product talk, but I realize that a lot of people might not be familiar with Azure DevOps. So it's Microsoft's CI/CD plus tool, let's say. We use it for the majority of the orchestration pieces. It has a ton of features in it. It used to be called Visual Studio Team Services or VSTS, but it has pieces for like issue tracking. It has pieces for pipelines or CI/CD. It has like an unlimited amount of Git or Git repos, and then various integration testing, smoke testing features, and then artifact or package feed storage. So yeah, it works really well as a solution because it played really nicely with some of the third-party tools, both the open source ones and the proprietary ones, and then as well as, of course, the Azure platform, where all of these models would live and running in production. And we primarily use Azure pipelines. So yeah, the next slide. If you were familiar with Azure DevOps at all, you know that there's the kind of the idea of the pipelines, build pipelines, and the release pipelines. It's actually been merged since then, but so in this case, within Azure pipelines, this was kind of the model training process that we used. So Translake already actually built that custom drift detection system in-house that I was mentioning. That drift detection system would actually start the process off. It would trigger the run of an Azure DevOps build pipeline, and that's just through like a basic REST API that DevOps exposes. And then essentially a list of models were sent from that drift detection system and then created, added as a variable group within Azure DevOps to store in that pipeline. And we came up with the idea of this, the Azure DevOps REST API, or we came up with the idea of the orchestrator build pipeline, and then essentially created that list of stops, did some of the retraining, and then triggered a pipeline per model on a per model basis. You can see all the models on the right there, or the pipelines on the right that it actually triggered. And then each model would get trained in Azure, evaluated, and then uploaded to that central model registry. That was done in Azure ML Service, the model registry. And if the evaluation piece was important, because if it was performing better than the model with the same ID that was already there, the metric, and then the metric that was used was the absolute error of the prediction departure times compared to the actual departure times. That's a question in the chat as well. And then we were using Azure Machine Learning Service. So there's like in the Azure portal, there's a UI that comes along with Machine Learning Service that you can see how the models are doing over time. And we also use some custom Power BI reports as well for the monitoring pieces there. So that was kind of the retraining, packaging up. And then of course you have to get to the deployment step. So there's also the idea of release pipelines within Azure DevOps. And that kind of started actually with a manual approval of batch. Transit kind of decided they weren't ready to go full CI/CD yet. And so we did a manual approval of that batch. And they also wanted to check that list of models that had been produced by the drift detection system. So yeah, these were triggered by a manual approval, and then those were all the stops and the segments models in there. And the idea was, at least at the beginning, so we created the orchestrator release pipeline, similar idea to the orchestrator build pipeline. It also add that list to its own variable group within Azure DevOps. And if you're not familiar with what variable groups are, it's just like variable, like sort of environment variables in a pipeline agent. And then that would trigger a pipeline per model, which would essentially get deployed to the QA environment first. And then there would be some smoke tests that would run on it, and then actually deployed right to prod, and then similarly some models on that. And so this was kind of the end-to-end workflow. Again, this like relied pretty heavily on Azure DevOps in Azure Machine Learning Service. Yeah, again, this was all the pipelines. The Azure DevOps pipelines were sort of the main scaffolding, if you will, and then the Azure Machine Learning Service was used some of the pieces. So in terms of the takeaways, because I think we are getting close to our time here, we just kind of want to share the profound impact that customer experience has on public transportation. So again, Translink went through a lot of work to get these models working pretty well for them, and they are in production, which is awesome. And then we also wanted to talk through just kind of the solution and benefits using the micro-model service approach in a machine learning solution. And then finally, the importance of that end-to-end machine learning ops process when operationalizing these machine learning models at scale and getting them all to work together. So yeah, thanks so much for coming to our session. I think there was a few questions in the chat to answer, but if you have any additional questions, like I think you can just ask them in the chat.
Or not good. So Alice, I guess we can go through on the top here. So I can probably start. So the first question, can a single stop be used for multiple routes? If so, why did you use a different model per route for that stop? Yeah, so through the micro model service approach, we definitely recognize that a stop can link through multiple routes. So you would definitely have a consolidated number of routes. So you would not have duplications like that. Yeah, and that's actually a core benefit, is that having this micro model service approach, you can leverage these run and dwell time predictions for multiple routes, even new ones for route planning purposes. Next question. Oh, sorry, Alice. I just realized you had answered that one already. Did we end up comparing models to baseline metrics such as average and standard deviation? So Translink actually defined a number of initial metrics like weighting the dark. So they actually compared based on the existing APIs and wanted to actually calculate improvements from there. So it was a very business-oriented metrics for performance.
Mm-hmm.
Alice, yeah.
Mm-hmm. And then the features used, the next one, I believe, we talked through that a little bit. Obviously, bus location, so like they still use the GPS of the bus. That had like the highest impact on the predictions. But then there was also weather data. There was significant traffic data, and then they used their schedule that they initially had as well as a feature. Am I missing any, Hubert?
Oh, I think
those are the main ones.
Yeah. How do we incorporate feedback? So that comes through the custom data drift monitoring system, and of course, there's also model performance that's tracked. So whenever new models are retrained, users can go through Azure DevOps to validate and approve any future deployments.
That's also why we had the manual kind of checks on there on the release pipeline. That's a good one. So there's a model per stop. Wouldn't the errors accumulate since errors add up as one model's prediction is used for the next?
Yeah, good question. So I would actually say it's the opposite. I'll give you an example, and this is it's actually quite interesting. So traffic, as we know, is the core predictor, right? It's, super important. Google Maps traffic, if you subscribe at scale, actually gets very expensive. So one novelty with this microservice model approach is that when you have a bus, it's the same route probably ran 5-10 minutes earlier, and those actually are proxies to traffic. So you actually have a fairly innovative way to provide a very good proxy for traffic based on previous actual bus departure time. So you can actually start linking in previous runs. So I would actually say this approach, where you have it granular at the stop level, you can actually start using previous great proxy for traffic, and that's what's done here.
Mm-hmm. So the idea of like sister buses, and then like which were on the same line, and then cousin buses would form different ones, but might go through the same stop. Things like that they used for traffic.
Yeah. So I think Andrew's questions was addressed.
Can errors be reported by users to pinpoint these? I don't think now. That's a good feature request. Hopefully the video wasn't flashing for everyone.
How many records did you? I think if that's about like just a number of rows in the data, I would say one example would be you're looking at potentially hundreds of thousands of records, if not even vastly more, because you would have very granular GPS locationing, and then every stop, every bus instance would provide actual departure times, which would be used. So it's quite a bit. So there's a good question, Alice. Can deployment be done through AKS?
Yeah, so great question. 100% yes. So how Azure Machine Learning Service usually works is there's like a ton of built-in compute options that you can actually choose, and AKS is one of them. Also, when in this specific case, we decided not to go down the containerization route. Those models were super tiny, and a container layer actually would have just added probably some additional stuff we didn't need. Honestly, those were tiny Python models stored in memory. But definitely, if there's a ton of benefits for containerization, and in this specific case, it wasn't. We decided not to go down the route. The team wasn't as experienced with Kubernetes, but in the future, definitely be a good idea.
Yes, the driver could be a feature. I think there's some, just overall there from that user perspective, we would definitely, recommend basically, just either leveraging just something like a driver ID or anonymization. But drivability is considered, but it is a sensitive topic for a number of machine learning use cases here. Yeah, so I posted the GitHub link. Yes, so for in terms of how busy the bus is, it's considered because that's part of the dwell time onboarding about how many passengers go onto the bus. So in Vancouver, there's the Compass system, which is the tap payment card, which provide that information.
So I think that's another maybe record or piece of data they used, which was the number of taps per day, which was really handy. How many total features? Wasn't there about 22 at one point, I want to say?
Yeah,
22.
Around that, I think, ballpark, yeah.
URL, yeah, this is Hubert created this machine learning ops URL. And again, a lot of I'll post another one in the chat here that we have, that MLOps one that Hubert has, but there's also a couple other machine learning ops resources we can point you to from like Microsoft, pretty much. I'll post those in a second here. How did you evaluate the accuracy for over 18,000 models? So those were done on an individual basis. I think I said it was, we decided, or TransLink rather, decided that they used the error, they tried to minimize the error in the departure time. So actual departure times, of course, was the real one, and then the estimated ones. So trying to minimize that.
Yep. So we addressed the traffic data. So just in terms of like data noise and data quality, I think it's average machine learning project in terms of that scope. So there was definitely concerns. Actually, there would Alice, I think they had ghost buses. Like sometimes, obviously in transit, the system thinks there's a bus coming, but there isn't, because that bus actually got canceled. So actually this project, I think, actually helped TransLink start to actually identify better what ghost buses were and when they actually would occur. So this actually almost helped them, like many other data science projects, actually helped address some of, or identify at least some of the data quality concerns.
Oh, wow. Benny's here. Benny, are you still here?
Oh,
you can answer that question way better than me.
Yeah. Great timing. Yeah. So we have our TransLink,
I guess,
can
you?
I don't know if TransLink can actually, sorry, Benny can actually, I don't know if he can speak, but I think he's posting. Yeah, so certainly.
Having me run the most with updated times and also how much computing power. Yeah, so Benny was just saying it's our first cross-department large-scale project. It's first large-scale machine learning project at TransLink. It's a collaboration between IT, QA, database specialists, research, and analytics team. Okay, cool. That's a great question. Do you need to recalibrate post-COVID? Benny, I would love to know the answer. What's happening there post-COVID, honestly, because obviously the ridership has gone down and the bus schedule has gone down. So if you had any insights there, I'd be super curious. We didn't use auto ML on this case. Yeah, so Nikki, the estimated dwell time based on the demand for the bus number of bus passengers was using that taps, like card taps. I think we mentioned that before, which is like if you've ever taken a bus in Vancouver, you have to like tap in with your Compass card. That's how that works. And so yeah, thanks everyone for coming again. We'll continue to answer some questions in the chat, and we have Penny here to help us do that. Yeah, during COVID, we took recent averages instead of ML. Okay, took COVID-19. That's interesting. I think we got questions. Hubert, was there any that I missed?
Model rerun. So there's two notions. There's the actual model prediction. So those are based on GPS updates. So those would actually occur very often. The model retraining part would be kind of staggered through potentially days, weeks, etc. So there's two notions of kind of rerun for models. The predictions themselves would get updated very often.
Oh, Benny, we can invite you to the video call. Yeah, I won't do that to you.
Yeah, that's probably no pressure. Right? Yeah, no, it's great. Yeah.
There's a drop in accuracy when you switch from machine learning to averages. Oh, for COVID. Great questions, everyone. Yeah, again, thanks for coming. Maybe we'll hang out here for like one more minute or two, and then probably jump off. Yeah, feel free to message Benny if you have any other questions. All right, thanks for coming, everyone. Yeah, I think if we leave the meeting, I think we kick people out. I think that's maybe what happens, but
okay.
Yeah, enjoy the rest of your day.
Yeah.
Bye.
Yeah, and again, thanks, Benny. So we'll have to catch up very soon. Bye, everyone.